Welcome to Paris Podcast number 112, and today we're talking about how 3D printing and airfoil affects its lift and drag productions. So to do that, we're going to look at a paper called Investigation on Surface Roughness of Polyjet Printed Airfoil Geometries for Small UAV Applications. So 3D printing, as I'm sure you'll know, is where you actually print an object in a material, typically plastic. So this means you go typically layer by layer, depositing this plastic, and you build upon this into the shape that you want. Now, the reason why this is important for not only aerospace, but really every industry, is that it dramatically increases what we can make. The problem with airfoils and for aerodynamics is that 3D printing is not technically very smooth, because you're doing it layer by layer, and there are a whole bunch of mechanical reasons and thermal reasons why there will be different layer, like the layers will not align exactly 100%. It means that there's a slight roughness to the surface when you finish it. Now, some 3D printers are incredibly good, but none are perfect. It's not like injection molding, where injection molding is pretty much what we always have with plastics, like consumer plastics, and they're very smooth. You can get very smooth surfaces out of them. 3D printing is not nearly as smooth, so the effects of these roughness layers and the location of these, like the direction of these layers, do they affect the airfoil performance? That's what we're looking at today. So this is open access paper, and you can find it in the link in the description. So let's get on with it. So different materials such as fiberglass, Kevlar, carbon fiber, and other materials such as styrofoam, wood, and plastics, and production techniques have been used for small UAV productions up until now. But with the advancements in technologies such as additive manufacturing methods, so 3D printing, we can also make UAVs out of this type of approach. Additive manufacturing is based on a layer-by-layer manufacturing. Unlike conventional manufacturing techniques, it has a very low buy-to-fly ratio. So what I mentioned, it dramatically opens the doors to what we can do cheaply. So we can do a whole bunch of prototyping in an afternoon, really, and it's very cheap and quick. Among these methods, polyjet technology has a very wide area of applications for polymeric materials. Polyjet technology is another name for material jetting process in which photopolymer materials are deposited on a build platform as droplets, and they form a very thin layer. Then UAV light is used to cure this material on the build platform. After curing a layer, the build platform is lowered with an amount of layer thickness, and the process continues by jetting new liquid material onto the previous layer. So what this means is, let's say you have a surface to your bed, and you squirt a layer of like a liquid, it's like a plastic liquid onto the surface. Then you have your UV light coming down and curing it for a certain amount of time. Then you move the bed down, or you move the nozzle up, whichever one, as long as the distance between the nozzle where the spray comes from and the bed increases. You then add another layer on top of the first layer, which is now solidified. You then hit it with UV again, and it cures, and then you do the same process again and again until you finally make your object. This is slightly different to the most common consumer 3D printing approach, which is called FDM. And this is the most common one. Like if you were to imagine what 3D printing is, you're probably going to be thinking of this type, which is where you have a nozzle, which is just squirting out liquid plastic again, but it solidifies immediately without the UV light. So you just deposit it. After a little bit of cooling, it will just solidify again. So if you go into YouTube and you type in 3D printing, this is the one that will come up almost all the time. Whereas this UV light one is used a lot more in industry, and this is mainly to get higher quality prints. So when all the layers are successfully cured, a full-scale part is obtained. Since the material used in this polyjet is in a liquid state, a support structure is needed, especially in overhanging regions, and these support structures need to be removed from the part after printing. So why is that? So if we were to look at this idea of when you deposit this fluid onto the surface to then cure it, if you have an overhanging region, so for example, let's say you want to make let's say just the Eiffel Tower or something. So you have the Eiffel Tower, and there are 3 levels to the Eiffel Tower. The first level is obviously hanging above just thin air. So if you were to print just like some plastic here onto this layer, it's just going to fall straight to the ground. That's why you need to have some supporting structure to be able to print on top of this. The supporting structure you then break off later. Why is this important? It's because this supporting structure can affect the surface finish, which we'll get into in a little bit. So in most of the studies and literature, it was stated that the highest surface quality of parts are obtained by polyjet technology. However, this quality or amount of surface roughness depends on different geometrical and process parameters. For example, tray location, build orientation, layer thickness, type of material, surface roughness, and surface finish settings, and post-processing are all parts of this process which can affect the surface roughness and often do. The effectiveness of these parameters on the surface roughness of polyjet printed parts has been investigated in the literature. So some researchers stated that the lower layer thickness of 16 micrometers, for example, and glossy surface finishes result in lower surface roughnesses. So how do you make a glossy surface compared to a matte surface in at least this printing process? That comes back to the supporting material. If you were to have complete supporting material around the entire object, then you break it off, that will leave a matte finish. If you have no supporting material, then that is a glossy finish because there's nothing touching that final layer. That's how you can get glossy compared to matte. Some other researchers stated that surface finish settings, such as matte or glossy, has the highest effect on surface roughness with a contribution of 95%. On the other hand, parameters such as layer thickness and build scale have very little effect on the surface roughness, with only about 3% of the total surface roughness coming from these parameters. That's a huge assertion, and that's probably due to when you have a very low layer thickness, so 16 microns instead of 100 microns. As you get a higher micron thickness, I'm guessing that this layer thickness plays an even more important role than only 3%. So locating the part along the X or Y axis of the build tray in a polyjet has some amount of effect on the surface roughness of the final part. So again, how you orient this part to be printed, whether it should be along the X-axis, Y-axis, or whatever. Some researchers stated that the best roughness results were obtained when the parts were placed close to the XY plane. So this is now the horizontal plane. Some other researchers stated that the part orientation and part size have the main influence, and part location on the build plate has a relatively lower influence on the quality of the polyjet printed parts. So in other words, all these researchers are just looking at different parameters of printing, and they're trying to assess what orientation, what settings will give the best or the worst results, the worst surface finishes. In other studies, the same authors stated that the build orientation and surface finish setting were the major factors affecting surface roughness, and maximum surface roughness was obtained for the 90-degree build orientation. What does that mean? I don't really know. I think it's mainly just printing along a certain axis. I'm not sure which axis that is, and it may be dependent on the printer that they have. Similar results were observed in another study where they stated that the surface roughness increased with an increase in the angle of sloped surfaces, and the best and worst values of surface roughnesses were observed when the angle of the sloped surfaces were 0 degrees and 90 degrees respectively. That makes a lot of sense. So let me break down what this means. Let's say you have a trapezoid that you're printing, a trapezoid prism, let's say. So the vertical sides are now at an angle to the ground. Let's say that could be anything. Let's say 20 degrees. So what this means is when you go up each layer, so you can break this trapezoid into a bunch of layers that you're printing in. Let's say it takes 100 layers of plastic to print this trapezoid. As you go up, each time you go up, the printer has to move to the side a little bit because now the walls have moved to the side because they go at an angle. So this means that each layer now has, if you zoom in, it has this stepping process because the printer is moving across each time and it's starting from a new location each time. And you're going to get this slight stepping because it's not finite. It's not infinite, sorry. It's a finite, it's a discontinuous process. It's not continuously just printing, if that makes sense. So you're going to be getting rough edges. What this means is if you can print something vertically or horizontally without much sloping to many angles, that's going to give you the best results. So in polyjet technology, two printing modes are used, high speed and high quality. The high quality is usually with the lowest layer thickness. High speed is usually when you put in a very high layer thickness. So that means you don't have to have as many layers, so you don't have to have many run-throughs, run passes, and you can get the print done quicker. Related with support strategies, matte and gloss surface finishes are used in polyjet technology where the whole part is covered with supporting material. So that's the matte setting, as I mentioned, or only the structurally needed areas are supported. So this is the glossy setting. Some researchers stated that the glossy setting resulted in lower peaks and valleys and therefore lower surface roughnesses than the matte surface finish. A similar result was found by some other researchers. This lower surface roughness with the glossy surface finish option resulted in higher fatigue life, as stated by other researchers. So why is that? Potentially because if you have more macroscopic roughness effectively, because if you have very rough surfaces, that's verging on macroscopic roughness, then you're going to get stress concentrators, I think. That's potentially why you're going to be getting a higher fatigue life with a glossy surface instead of a matte surface. However, if you have any other ideas about this, let me know in the comments below. The surface roughness characteristics of airflow impacted areas, such as wings, are directly related to the performance of UAVs. Airfoils and airfoil-like geometries are very important in the aviation industry, and the surface roughness of these geometries directly affects aerodynamic performance. To the best of these authors' knowledge, the available scientific literature has a gap for polyjet printed airfoil geometries and their surface roughness characteristics and performance. To fill this gap, this study focuses on producibility and surface roughness of airfoil geometries in polyjet printing. Two different tray orientations, so either in the X or the Y direction, two different build directions in the horizontal or vertical, and two different surface finishes, so matte or glossy, were used to investigate the effect of these parameters on the surface roughness in the end. So in other words, how you're printing this object, how is that affecting the surface roughness, and in the end, how is that affecting the lift and drag performance of these airfoils. They're using CFD so what they do is they print these airfoils, they then measure the roughness of these airfoils, they put it into the CFD, and then they do these simulations on these airfoils to see what the effects are on this lift and drag. So let's talk about the methods and materials. They are using a NACA 0008 airfoil, which is a very thin symmetrical airfoil. It's only 8% thickness to chord ratio, and it's significantly thinner than most airfoils you come across, and it's symmetrical, so there's no camber. So that means at 0 degrees angle of attack, there's no lift. At high quality printing modes with 16 micron layer thicknesses were used to obtain better surface finishes. So 16 micron is very good. Most consumer printers will only go down to about 100 microns. If you make your own 3D printer or modified 3D printers, you can get it lower. For example, I made a 3D printer a while, over 5 years ago now, I could put it down to about 10 microns comfortably. I was playing around with 5 microns, but then the cooling rates were not nearly as efficient, as good as what they needed to be. So 10 microns is the lower that I found for building your own, but 100 microns is like out of the box standard. 16 micron is like an industry standard for polyjet 3D printers, and it's very smooth. Both matte and gloss surface finish options were used in this experiment. After printing airfoil geometries, support structures were removed with sodium hydroxide solutions. So what this means is they're printing the object and they have the support structures to support the overhanging areas or the very angled areas, and they're printing this in a different material. Then you put it into a bath of sodium hydroxide in this case, and that dissolves the supporting material, leaving you only the part that you want, because that part that you want was built in a different material. So that's a pretty cool technology, which you often use with ABS as well. If you were to have a 3D printer yourself, the best situation with ABS is when you have a dual extruder. So you have one extruder which is printing in ABS, the other extruder is printing in another material which is soluble in a certain solution. You print the supporting structure in that soluble material. You then print the other part in the non-soluble material. Then when it's done, you just give it a bath and you're good. For vertically oriented samples, surface roughness measurements were performed on 2 sides of the surfaces and at 3 locations along the X, Y, and Z axes. On the other hand, for horizontally oriented samples, surface roughnesses were measured on 2 surface sides, so the upside and downside, so the suction side and pressure side, and at 3 locations along the X and Y axes. The average of 3 surface roughness measurements were used in the evaluations. So figure 3 shows the orientation of these airfoils. They are very thin airfoils, as I mentioned. They have 4 which were printed vertically, 4 that were printed horizontally. What this means is that for the vertically printed airfoils, they started with the wing root effectively. They printed that first layer, and as they go up and up, you get to the wing tip. For the horizontally printed airfoils, you actually start at the wing pressure side, and the more layers you go up, the further you get to the suction side. There are two different ways of printing these things. So let's talk about the numerical analysis, their setup. According to the velocities of the UAVs in the literature, 3 different velocities were selected to categorize the velocity of fixed-wing UAVs. So 90 kilometers per hour, 65 kilometers per hour, and 40 kilometers per hour. And these were categorized into high-velocity UAVs, mid-level velocity UAVs, and low-velocity UAVs. According to the defined velocities, the calculated Reynolds numbers for these UAVs were 27,000, 44,000, and 60,000, respectively. So interestingly, the critical Reynolds number, in generally speaking over a flat plate, ranges from 100,000 to 3 million. So what this means is that the critical Reynolds number is where the Reynolds number at which transition will occur from laminar to turbulent. Now, of course, this is quite a difficult thing to quantitatively measure, and we often just quote a general range. So we say like, okay, transition occurred around 150,000 Reynolds number to maybe 200,000 Reynolds number. But they could be very low, so it could be 100,000 up to 3 million if you have a very low thermal density flow and a very low surface roughness. For airfoils, they say that the critical Reynolds number typically ranges from 1,000 to 20,000 based on this particular profile, so this NACA 0008. So that's much lower. What does this mean? It means that for these Reynolds numbers that they're looking at, this is smack bang in the middle. So these are in the transitional regimes, and depending on the surface roughness, you could get a turbulent flow over the airfoils or still laminar. So this is quite an interesting area to look at. Moreover, these 3 types of velocities were utilized as the free stream inlet velocities for the 0-degree angle attack case, and they also looked at the case for -5 degrees to 30 degrees in 5-degree increments with these different surface roughnesses at these different velocities for these UAVs. So what about their CFD setup? The flow type was determined as turbulent flow according to the Reynolds number. So potentially turbulent, potentially transitional, in my opinion, because they mentioned here that the critical Reynolds number ranges, in this particular case for this airfoil, from 1,000 to 20,000, whereas their 1,000 to 200,000, whereas their airfoils range between 27,000 and 60,000. So that's between this range of transition. So it could be laminar, could be turbulent. They're assuming that it's turbulent. That could potentially be a bad assumption, but we'll cover in a second why it's actually okay. It's a bad assumption, but the consequences are not anything. So it's not a problem that they made a bad assumption here. And the reason why is because they say ANSYS documentation suggests that the realizable K epsilon or the SST K omega turbulence models for the analysis of standard cases in which surface roughness effects are also taken into account are good. So using either the realizable K epsilon or the SST K omega turbulence models for RANS simulations are the most accurate. So they chose to use the SST K omega model instead of the K epsilon model in this study, which is still fine because the SST K omega can handle transitional flows as well as quite laminar flows. So even though they made that bad assumption that the flow was, they assumed it to be turbulent, even though it could be turbulent, could be laminar, could be transitional, still they're using the SST K omega, which is a very robust model, and they don't have to worry about that assumption anyway. So they're sticking with the SST K omega turbulence model, which I've talked at length about at other podcasts. I won't go into it here. Let's move on. So how do you model the surface roughness? They say to model the surface roughness for the flow analysis, 2 roughness parameters needed to be specified. The first one is the roughness constant, and the default value of 0.5 denotes uniform roughness. So if you were to change it away from 0.5, it means that there's less uniformity. So in this study, they use 0.5. And another parameter that they need to specify for the roughness is the roughness height, Ks, as in denoted, the default value of which is 0, and this denotes smooth walls. For experiencing the effects of surface roughness, the value of roughness needs to be greater than 0 of this roughness height. Some methods are utilized for calculating the roughness height. However, some studies show that the arithmetic mean deviation of the assessed profile has a correlation with roughness height. In this analysis, the roughness height to the arithmetic mean deviation equals 5.2, and they're using this as this value now. So the surface roughness measurements were broken down into 3 groups: smooth, mid-level roughness, and high roughness. Thus, the 3 different arithmetic mean deviations included 0, so that's smooth, then the mid-level roughness, which was 88.2 microinches, then the high-level roughness, which was 265 microinches. So these are the other parameters that they're specifying in their CFD to get this roughness. So that's the CFD setup. Let's talk about the results now. So the production on and surface roughness results. So in figure 5, they show all the specimens produced after removing the support structures. As seen, vertically oriented parts show a very high amount of distortions, especially in their trailing edges. So you can see in these figures here. If you're listening to this, by the way, you can watch the video on YouTube or the video on Spotify, or you can download the paper. If so, we're looking at figure 5, and we can see that the trailing edge is very warped. Like in some points, it even looks a little bit broken because it's so brittle. And they say that as the vertical oriented parts show very high distortion, especially in the trailing edges due to small size of the trailing edges and the slenderness. Furthermore, very high surface irregularities were observed on the side walls of vertically oriented specimen. Moreover, no visual print problems was observed on the horizontally oriented specimens. So if we go down to these horizontally printed ones, the trailing edge looks very nice and smooth. And although that one looks a little bit warped, but overall they look much better than the vertically printed ones. So why is that? Now, I actually have quite a lot of experience printing airfoils because that's what I do in my spare time. Anyway, with this particular case, so they also mentioned that it depends on the orientation of the airfoil, but in my experience, it also depends on the layer thickness. So the reason why is I mentioned earlier that I've made a printer that can print down to 10 microns and comfortably, and even down a little bit lower if you really, really tweak it a lot, but 10 microns comfortably. What I've noticed is if I print an airfoil, regardless of whether it's horizontal or vertical, with a very low layer thickness, so 10 microns, I'll start to get a very warped trailing edge, especially if it is in this vertical situation as opposed to horizontal. But either way, there will be some warping. If I then put the thickness of the layer up to 100 microns or even 50 microns, that warping really gets cut out completely, like 99%. So I think it's not only due to this orientation, but also due to the layer height. If they were to make this layer height thicker, you'd probably be able to print this airfoil in a vertical position without getting this warped trailing edge, I think. But regardless, they're using a very fine layer thickness just to get a very smooth surface, which then results in these problems. So, let's talk about the numerical analysis results. 3 different velocities were applied at inlet velocities of 40, 65, and 90 kilometers per hour, and these correspond to low, moderate, and high velocity UAVs. Figure 4 shows the surface roughnesses of all these airfoils in the different directions. It is showing that the high amount of surface roughness values were observed in the vertically oriented samples, specimens 1 to 4. Let me go down a little bit. Here we go. For vertically oriented samples, when measurements were performed along the x-axis, parallel to the build direction, a higher amount of surface roughness values were observed than values taken along the x or y axes. This is due to the nature of the layer-by-layer manufacturing and stair-stepping effect of polyjets. So what is stair-stepping effects? So it comes back to this figure here that I drew earlier, where when you have a change in the cross-sectional area of an object as you go up, the printer head has to move a little bit. So it has to move to the side just to either increase the cross-sectional area or reduce it. As such, you get a stair-stepping effect where it's now not smooth. It's not going to be a completely smooth line, but because you're going up in a certain height, let's say here at 16 microns, if you go up 16 microns, you have to go to the side a certain amount to accommodate this change in geometry. So you get this stair-stepping effect, which results in roughness. So they say some deviations in the surface roughness results were observed, especially in the vertically oriented samples, due to the overall geometric deviation and distortion of these samples. Table 5 shows the surface roughness effects on the lift and drag values at different velocities for 0-degree angle attack. They say you can see that the lift is dramatically reduced for the, but okay, so I should mention that this is at zero angle of attack, which means that there should be no lift at all. So even though there is a massive reduction in lift for all roughness surface, for all rough airfoils, that doesn't really make a difference because it should have 0 degrees and should have 0 lift anyway. The drag is more important. So what we see is as we go higher in the velocity, more roughness, like a rougher surface, results in more drag by up to 10%, up to 7.5%. Now in Figure 6, they say that Figure 6 shows the effects of the surface roughness on the lift coefficient with angle of attack. Generally, there are 3 main phases. The first is during regular lift production, i.e. pre-stall range. In this range, there is little difference in the lift coefficient with surface roughness. However, as angle of attack starts to reach stall, these differences start to grow with surface roughness, typically reducing the lift coefficient. This reduction hovers at around 2.5% for the mid-range roughness airfoil and 5% for the rough airfoil. As the angle of attack goes higher, interestingly, the lift coefficient maintains a high value despite being well within the stall regime. For example, the stall is arguably starting at about 10 degrees. However, even at 30 degrees, a considerable amount of lift is still being produced. As a side note, I think there are also typos in the y-axis. I think these values should actually be about 100 times greater than what they are. So instead of 0.02, it should be 0.2. So I think that's just a typo there. But we can see that the surface roughness is typically reducing the lift at higher angles of attack, so that's not good. Figure 7 shows the drag coefficients of the smooth, mid-level roughness and high roughness airfoils with changing angle of attack. When the roughness airfoil experiences significant lift coefficient reductions nearing the stall and in the stall regime, unfortunately the drag coefficient is also increased. So there is a double disadvantage where not only is the lift coefficient worse, the drag coefficient is also worse. What's more, even the mid-level roughness airfoil experiences a worse drag as well. So the drag increases are seen even at quite low angles of attack of 3 to 4 degrees, with the roughest airfoil routinely increasing the drag coefficient by 5%, while the mid-level roughness airfoil increases the drag coefficient by about 2.5%. So overall, we can say that roughness is bad for the airfoil performance. It reduces the lift, generally speaking, and reduces the drag coefficient across the entire range of operating conditions. Now, let's go to the discussion. They say Figure 8, let's move to Figure 8 here, shows the surface roughness measurements on both sides of all specimens, and it is clear that the surface roughness measurements along the z-axis for specimens 1 to 4, which were printed vertically, remember, are higher than measurements along the x or y directions due to layer-by-layer manufacturing and the stair-stepping effect. For specimens 5 to 8, which were printed horizontally, surface roughness measurements along the x direction are lower than the y direction. So it can be seen from Figure 8 that up-facing surfaces have lower surface roughness values than down-facing surfaces due to the fact that up-facing surfaces are naturally supported by previous layers of the same material, but down-facing supports have the support of different materials. So what this means is a few things. First of all, if you have your airfoil printed vertically, so it's printing like this, the surface roughness is worse than if you have it printed horizontally. Also, the horizontal airfoil, the surface roughness on top is smoother than underneath because underneath you have overhanging regions. If you were to think, how would you print this? Like if you're depositing material, it's just going to fall to the ground. So what you need to do is you need to print a supporting structure as well to hold up this first layer. So you print on top of this supporting material, then you break this material off afterwards, or dissolve it in this case, and you're left with this bottom surface. The problem is that this supporting material is not it's not another complete surface, so there is going to be some sort of roughness underneath due to this. So that's why we get a greater roughness underneath than on top. So for all specimens and surfaces, the lowest surface roughness value, was observed on the up-facing surface of specimen 6, where the specimen was located along the x-axis and the horizontal build orientation, and a matte surface setting was used. So interestingly, when you print an airfoil horizontally, so the leading edge and trailing edge are at the exact same height of the printing surface, that is far smoother than when you were to print it vertically, and by like a factor of 6. So like the surface roughness of these horizontal airfoils are like 15 or 20% of the surface roughness of the vertically printed ones. It's a massive difference. It's clear as day. So what is the effect of the tray location on the specimen's surface roughness? Figure 8 reveals that when build orientations and surface roughness settings are the same, printing along the X direction in general results in parts with lower surface roughness than parts printed along the Y-axis. So this is also stated by other researchers that the distribution of the same parts on the build surface can affect mechanical properties due to the over-curing of some parts in different locations while other parts are being cured. So what this means is, let's say you have one layer and you're now curing this, the left side of it, and you move the light along or whatever how you're curing it. As you get to the end and you're still curing, this part has already been cured and it's now being over-cured, which changes its mechanical properties compared to this one, which is just being perfectly cured. So that difference can result in different surface roughnesses and different mechanical properties. So that's a major point to consider when you're printing. Other researchers stated that parts printed along the x-axis gave the best results in terms of stiffness. According to the results of the present study and the available literature, it can be suggested that for better surface quality and surface roughness and strength, airfoil geometry should be printed along the x-axis when printed in polyjet. So, what about the effects of the build orientation on the surface roughness? They say it can be seen from Figure 8 that when the tray location and surface finish settings are the same, horizontal build orientations resulted in parts with lower surface roughnesses than vertically oriented parts. These results have good consistency with literature. Since vertically built specimens have a high amount of distortion, especially at the trailing edge, and higher surface roughness values, it can be concluded that, or can be suggested that the better surface quality and lower distortion, airfoils should be printed in the horizontal direction in polyjet. That's also generally speaking for FDM as also regular consumer printers. If you have a 3D printer yourself, I would suggest printing it horizontally as well. You'll get a smoother surface that way, in my experience as well. So that's not just polyjet specific. So what about the effects of surface roughness, of surface finish settings on the surface roughness? As stated before, in the matte setting, the whole part is covered with a support material, and in the glossy setting, only structurally needed areas are supported. For this reason, it is more meaningful to see the effect of the surface finish setting on surface roughnesses for the up-facing surfaces of specimens 5 to 8. The reason why this is because all specimens here had some sort of support material. Specimens 5 to 8 had support material underneath because they needed that to support that pressure side to begin with. The top surface, though, didn't have any support material because it didn't need it. It had the other layers underneath to support it. So based on the comparison between surface roughness measurements on the first surface of parts 5 to 8 and 6 and 7, where tray locations build orientations were the same, and only surface finish settings were changed, it can be stated that, in general, glossy surface finish settings showed better surface qualities than the matte surface finishing. But it is also clear that this situation depends on the location of the specimen on the build plate. Therefore, it can generally be suggested that for better surface quality, airfoil geometry should be built with a glossy surface finish. So, in conclusion, the experimental part of the study focused on the effect of the tray location, build direction, and surface finish options on surface roughness values of airfoil geometries printed in polyjet. Two sides of airfoil surfaces were measured along with two crossing directions. The numerical part is focusing on the aerodynamic performance of the polyjet printed parts in terms of different surface roughness profiles in the flow directions, velocities, and angles of attack. The following findings can be drawn from this study. So the airfoil geometries located along the X direction have lower surface roughness values compared to when printed along the Y direction. Therefore, it is suggested to print airfoils along the X-axis for better quality. Airfoil geometries printed vertically have very high distortions, especially on the trailing edge, and higher surface roughness values than geometries with horizontally built surfaces. Therefore, it is suggested to print airfoil geometries with horizontally built orientations for lower distortion and better quality surfaces. It was observed that matte and glossy surface finish settings resulted in different surface roughness values in different surfaces. And it is very difficult to make a correlation between surface finish settings and surface roughness. However, in general, it can be suggested to print airfoil geometries with glossy surface finish settings for better surface quality. Finally, surface roughnesses of the polyjet printed fixed-wing UAVs affect the drag by 7.5% in high-velocity cruises. Thus, convenient build orientations should be selected to reduce the surface roughness for increasing aerodynamic performance. By this, the limited cruise distance of UAVs can be increased. Thus, it is suggested that the build configuration of including y-axis tray location, horizontal build orientation, and matte surface finish settings is the best option for aerodynamic performance in terms of surface roughness with the least roughness in the flow direction. So, that's it in this podcast. I hope you liked it, and it's pretty cool because it's 3D printing for airfoils, which is, airfoils are cool, 3D printing is cool, all of it's cool. And if you did, make sure to like, subscribe this, and check out our other podcasts. And if you want to get better at CFD and or theory, check out our courses in the link in the description. And if you want to make your experiments 2 to 4% more accurate, check out the atmosphere Hall. The reason why it makes your experiments 2 to 4% more accurate is that the density of air changes by that much on a regular day. So if you were to come into your lab at 9 a.m., the density of air is one value. When you come back after lunch, it'll be another value. If you don't take account of these changes, then your experiments have these errors in them. And 2 to 4% is just on a regular day. Between days, weeks, months, seasons, it changes even more than that. 50% is not uncommon, and it's actually quite expected between months and seasons. So your experimental values, your data is going to be that much wrong. The Atmosphere Hall gets rid of that error for you, and you can find that in the description below. And it also makes your CFD validation data more accurate because everyone uses data for CFD validation. If you have your experimental values which have this error from the density included, you don't know that. So when you go into your CFD, the density of air you're using in that is different, and you're not even aware of that. That's why it makes CFD validation so much more difficult. So the Atmosphere Hall gets rid of those errors for you as well. Check it out, and I'll see you in the next podcast. Peace out, amigos.